We light sparklers and crackers during celebrations. Do you think metals can catch fire? It is safe to conduct this experiment in a fume cupboard and using proper goggles and a Bunsen burner. Take magnesium ribbon. Cut a piece of magnesium ribbon. Hold the tip of the magnesium ribbon using a pair of tongs. Burn it in a Bunsen flame. The tip of the magnesium ribbon burns with brilliant white light. The ash collected on the tray is magnesium oxide. Metal combines with oxygen to give metal oxide. When we heat copper in air, it combines with oxygen and becomes black copper oxide. Similarly, aluminium reacts with oxygen and forms aluminium oxide, also called alumina. On exposure to air, aluminium forms a white layer because of its reaction with oxygen. This white layer is a layer of aluminium oxide, also called white rust. This oxide coat over aluminium protects the metal from further rusting or corrosion. Anodizing is a technique of protecting aluminium by forming aluminium oxide electrochemically. The aluminium object to be protected is made the anode, and another aluminium plate is kept as the cathode. Sulfuric acid is the electrolyte. When a current of suitable voltage is passed through the metal, oxygen is evolved at the surface of the anode and forms a white film of aluminium oxide. This white layer of alumina is porous and adsorbs dyes of attractive colors. We can hardly avoid anodized aluminium articles in our daily life. Your mobile phone is also made of anodized aluminium. What is the nature of this metal oxide? Metallic oxide is basic in nature since it reacts with acid. Example, copper oxide. Alumina reacts with acids and also with bases. That is why aluminium oxide is amphoteric, that is, it is acidic as well as basic. Drop the gold ring into the water. Nothing occurs. Let's drop a piece of sodium metal. Metals are arranged in a table, the activity series according to their reactivity. Potassium and sodium are at the top because they are the most reactive metals. Gold and platinum are at the bottom because of their low reactivity. Metal reacts with water to give metal hydroxide and hydrogen gas. Potassium reacts violently with water to give potassium hydroxide and hydrogen gas. Similarly, sodium reacts with water to give sodium hydroxide and hydrogen gas. Hence, we should keep them away from air and water. Can you guess how we can protect sodium and potassium from moisture and aerial attack? We keep potassium and sodium immersed in kerosene. In this way, we can prevent them from coming into contact with moisture and air. Calcium reacts with water to give calcium hydroxide. Magnesium reacts with cold water slowly, but reacts with steam aggressively. Aluminum, zinc and iron react slowly with steam. Silver and copper do not react with water but are affected by air. Gold is not affected by water or air. Non-metals are not affected by water, example sulfur and phosphorus. Examples of magnesium, copper and sulfur powder in different test tubes. Add 5 ml of dilute hydrochloric acid to each of the test tubes. After a few minutes, bring a burning matchstick near the mouth of each test tube. What is your inference from this experiment? Not all metals react the same way with hydrochloric acid. When the matchstick was brought near the test tube containing magnesium, there was a pop sound before the flame went out. Magnesium reacted with the acid to produce magnesium chloride, a salt. Hydrogen gas was released and burned with a pop when the matchstick was brought near it. Most metals react with sulfuric acid to give metal sulfates and hydrogen gas. For example, copper reacts with sulfuric acid to give copper sulfate and water and liberates sulfur dioxide gas. Watch this experiment. You can see copper reacting vigorously with nitric acid. It forms an irritating brown gas. It is poisonous nitrogen dioxide. Experiments of this type must be conducted only in a fume cupboard. When the solution is further diluted with water, it develops into a blue solution of copper nitrate. Copper is oxidized and nitric acid is reduced in this reaction. Gold is dissolved neither in concentrated hydrochloric acid nor in concentrated nitric acid, but in aqua regia. It is a freshly prepared mixture of concentrated hydrochloric acid and concentrated nitric acid in a 3:1 ratio. Aqua regia is also called royal water, since it dissolves the royal metal gold. Group 18 elements are called noble elements. Let us take the example of neon. Neon has 10 electrons and 10 protons. The K shell contains 2 electrons and L shell has 8 electrons. This electronic configuration of the neon atom is very stable. All elements try to achieve the stable electronic configuration of the nearest noble element. Let us take the example of sodium. The sodium atom has 11 protons and 11 electrons. There are 2 electrons in K shell. There are 8 electrons in the L shell. The last electron is in the M shell. This is an unstable electronic configuration. The sodium atom gives up its outermost electron. Now it has 10 electrons, but the number of protons is still 11. Sodium becomes a positively charged ion, called cation. The sodium cation has a stable electron configuration. Now, let us consider a nonmetal, chlorine. An atom of chlorine has 17 electrons and 17 protons. The chlorine atom has 7 electrons in the M shell. This is a very unstable electron configuration. Chlorine can achieve a stable 2, 8, 8 configuration by gaining 1 electron and forming an anion. The two oppositely charged ions attract each other with strong electrostatic forces to form an ionic compound, sodium chloride. Sodium chloride exists as aggregates of oppositely charged ions. How do you think magnesium will react with chlorine? Magnesium has 12 electrons and 12 protons. Is this an unstable electron configuration? Magnesium gives away 2 electrons from its outer shell to achieve an octet. A chlorine atom needs 1 electron for stability. Hence, 1 magnesium atom combines with 2 chlorine atoms to form magnesium chloride, an ionic compound. Solid at room temperature. Let us see what happens if we whack a crystal of sodium chloride with a hammer. The crystal shatters. Why? Let us try to investigate some other properties of ionic compounds, taking the example of sodium chloride. Ionic compounds have very high melting points and boiling points. Melting point of sodium chloride is 1024 Kelvin. Electrovalent compounds are generally insoluble in kerosene and petrol. They are soluble in ionic solvents, such as water. Solutions of ionic compounds conduct electricity. Ionic compounds also conduct electricity in the molten state. Does solid sodium chloride conduct electricity? Ionic salts impart a characteristic color to the flame. Sodium chloride burns with a bright yellow-orange flame, and copper chloride with a bright green flame. Therefore, the flame test is used to identify the elements in an ionic compound.
Finite resource and non-renewable. Once used, they are gone and will not be replaced.
The growing need of iron exceeds 800 million tons every year. If it goes on in this rate, iron ores will be exhausted in 100 years. Copper, zinc, lead and tin may not last even for 50 years. Indiscriminate use of metals leads to depletion. Hence, there is a need to conserve metals. Activity series is a table that helps to predict which metal can displace another metal. Using this table, metallurgists can adopt suitable technique in the process of extraction or purification of metals and this in turn can help us conserve metals and use them more optimally. Zinc will displace copper from copper sulfate solution since zinc is more reactive than copper. Similarly, black silver deposits are obtained when a copper rod is dipped in silver nitrate solution. Copper plate is placed in silver nitrate solution. What do you observe? The colorless solution turns into blue due to the formation of copper nitrate. There is a black deposit noticed at the bottom. Freshly formed silver undergoes oxidation rapidly and gives a black deposit. This principle is used in oxidized silver jewelry. We can write the reaction as given in the visual. When two metals are involved in a chemical reaction, one metal replaces the other metal. But how can we find out which metal will replace the other? Metal that is more reactive displaces the less reactive metal. Can iron displace copper? Yes, iron can displace copper in copper sulfate because iron is more reactive than copper. The reactivity series of metals helps us to understand this. The following activity will also help us to understand this. Take a solution of copper sulfate in a beaker. Drop an iron nail into this solution. Leave the beaker undisturbed for some time. Iron displaced the copper in the solution, resulting in the formation of iron sulfate. This displaced metal is deposited on the iron nail as copper. The copper sulfate solution turned pale green to indicate the presence of iron sulfate. Thus, iron, which is more reactive, displaces copper. However, copper cannot displace iron as it is less reactive than iron. The more reactive metal, which occupies a higher position in the reactivity series, pushes out the less reactive metal and forms its own compound. This is called metal displacement reaction. Magnesium is more reactive than iron. So, magnesium can displace iron.